So we're looking at a paper today titled EnvHarness Awakening Static Worlds for Agent Learning. It was published in August 2026 by researchers from WashU, Google Cloud AI Research, and UNC Chapel Hill. And for this deep dive on AI paper slop, we're getting right into the core problem with LLM agents, which is that they currently learn by interacting with these static hand-built environments. So think of, WebArena or SWE-Bench.
Right, the standard benchmark.
Exactly. And the fundamental bottleneck here is that once an agent improves beyond a certain threshold, those static worlds are just, they're exhausted. They offer no new learning signal at all.
Yeah, they just plateau.
Right. So the prevailing alternative has been to use automated environment generation. But that relies heavily on LLMs to build new tasks and, crucially, to write the code that actually verifies if the agent succeeded.
Which is a huge issue.
Yeah, it leads to hallucinated evaluation metrics and just, domain-specific fragility. So this paper introduces EnvHarness, which is a programmable layer that wraps an existing static environment. It dynamically mutates the initial state distributions, the interaction rules, and even the task chains. And it does this purely at the API interface level.
Oh, that's clever.
Yeah, the system targets an agent's specific cognitive weaknesses. So it provides a continuous adversarial learning signal while perfectly preserving the original deterministic verifier of the underlying environment.
And, the broader context here that makes this so necessary is the severe engineering friction associated with constructing reinforcement learning environments for language agents.
It's a nightmare, right?
Oh, it's incredibly resource intensive. If you are training a policy, the state space explosion that is just inherent in something like web navigation or software engineering makes building high-fidelity Markov decision processes just astronomically difficult.
Because you're essentially hard-coding reality.
Exactly. You are hard-coding a highly complex state machine, and then you have to write a deterministic ground truth verifier to track the entire state transition matrix. I mean, that represents months and months of manual engineering.
Yeah.
Because of that overhead, the community just defaults to a handful of static benchmarks, and the obvious fallout from that is curriculum plateau. The agent solves the benchmark, the gradient flatlines, and the environment becomes effectively useless for any further optimization.
It's honestly the reinforcement learning equivalent of a video game, where the enemies are just hard-coded to level 1 forever.
That is a perfect way to put it.
Like, you optimize your policy to clear the initial bottleneck, but because the environment's complexity is frozen, your policy's capability just freezes right along with it. And we do see researchers trying to bypass this.
Right, with procedural generation.
Yeah, systems like SWE Smith or Genève.
Yeah.
And they attempt to procedurally generate new MDPs.
Yeah.
But those systems, they just kind of collapse under their own weight, don't they?
They do, yeah.
Because they require LLMs to generate the reward functions themselves. So you end up with this compounding error rate where you're trusting an autoregressive model to reliably evaluate the reasoning trajectory of another autoregressive model.
The methodological risk there is massive. You get what we call silent failures. So the generated verifier code contains logic bugs, and that results in false positive rewards.
Oh, so the model thinks it's learning, but it's just exploiting a broken test.
Exactly. And to mitigate that, you have to overgenerate environments and run this really aggressive heuristic filtering, which just completely destroys your compute budget.
Right.
But the conceptual pivot in this paper bypasses that entire pipeline. The authors essentially observed the architecture we use for the model itself. So think about tools like EnvHarness, right?
Okay, yeah.
Where we take a frozen set of model weights and we wrap it in a programmatic harness to provide memory buffers or API calling capabilities. Well, they took that exact same structural paradigm and applied it to the environment side of the equation.
So they just leave the underlying MDP completely untouched.
Completely untouched.
That is so elegant. EnvHarness basically operates entirely as middleware. It's intercepting the standard OpenAI GEM-style API interface.
Right, the standard interface.
Yeah, it sits between the agent and the environment, and it hijacks the reset, step, and observation functions. This allows you to dynamically reshape the state distribution and the transition dynamics without altering the core simulation at all.
You don't rewrite a single line of the ground truth verifier.
Let's break down the execution of that middleware, because the paper categorizes these interventions into 3 specific plugin components. They call them the stage, the contract, and the chain.
Okay, yeah, let's get into those.
So looking at the ALF World benchmark as an example, where a baseline task is simply, put a clean mug on the desk, the native environment's reset function just spawns the mug in plain sight on a countertop. How does the stage component mutate that initial distribution?
Well, the stage component overrides the reset function to manipulate the starting state of the simulation before the agent even receives its first observation.
Oh, sneaky.
Very. So rather than returning the default environment array, the stage executes a hidden trajectory of valid actions in the background.
Wait, what does it actually do?
In that ALF world scenario you mentioned, upon initialization, the stage autonomously fires off a sequence of commands. It navigates to a drawer, it opens it, places the mug inside, and closes it. So by the time the reset function actually returns the initial observation to the agent, the mug is completely hidden.
Wow, okay. Which shifts the agent's required capability from simple object manipulation to active spatial exploration.
Exactly.
You are expanding the required reasoning horizon without modifying the underlying reward condition at all, because the verifier still just checks if the mug ends up clean on the desk.
The goal remains identical, yeah, but the trajectory required to achieve it has been intentionally convoluted. Now, the second mechanism, the contract, handles the transition dynamics. It does this by overriding the step and observation functions.
So this is during the actual run.
Right. A contract applies a highly specific filter to either the action space available to the agent or the observation space returned by the environment.
Okay, give me an example of that.
Well, say you want to force an agent to operate under strict partial observability. A contract can intercept the standard room description returned by the simulator and run a truncation script, limiting the string to just 2 sentences.
Oh, wow. So the agent is forced to execute more exploratory steps just to build an internal state representation.
Exactly. And on the action side, a contract might institute a prerequisite dependency. So it could outright block the clean mug command unless the agent's action history confirms it is actually holding the object.
Okay, this is where I want to push back on the architecture a bit. Because specifically regarding the state consistency between the wrapper and the underlying simulator, if a contract intercepts the step function and arbitrarily blocks an action that the core MDP considers perfectly valid, doesn't that inherently desync the internal state?
That's a really common question, yeah.
Because if you mutate reality at the interface level, how does the original ground truth verifier at the core of the simulator still accurately evaluate the final state? Like, doesn't it break?
No, it doesn't break, and the integrity of the verifier is preserved because the EnvHarness middleware operates strictly as a string-based interceptor. It returns synthetic observations without passing the blocked action down to the core simulator at all.
Wait, really?
Yeah, so when the agent attempts an action that violates a contract, like, trying to clean the mug without holding it, the middleware catches the string, evaluates it against the contract's logic, and returns a natural language error directly to the agent, like, error, you must pick up the mug first.
Oh, so the core MDP simply doesn't register that the invalid action ever occurred.
Exactly. The simulator's internal clock and state tracker remain completely oblivious. To the underlying environment, the agent is simply pausing or processing. It only registers the actions that the middleware eventually allows through.
That is fascinating.
And because the ground truth verifier is only checking the terminal state of the core simulator, it remains completely isolated from the constraints imposed by the contract. The evaluation is 100% deterministic and reliable.
That string interception model makes the third component, the chain, highly scalable then, because the chain overrides the terminal conditions to basically concatenate multiple independent environments into a single extended trajectory.
Right, it strings them together.
So you complete the ALF world mug task, and the middleware suppresses the termination signal, instantly loading the state space for a secondary task, like, I don't know, operating a microwave.
Yes.
And the reward signal is only passed to the agent when the independent verifiers for both underlying environments return a success state. It is a brilliant way to test context window degradation and goal persistence over really long horizons without having to hand code a massive multi-room simulation.
It directly addresses those context switching failures we frequently observe in long horizon planning. But, the real engineering value of EnvHarness isn't just that these wrappers exist.
Right.
Because manually writing custom Python classes for stages, contracts, and chains for every single behavioral flaw an agent exhibits, well, that would just shift the engineering burden from the environment to the wrapper.
You'd still be coding forever.
Right. So the paper solves this by introducing EnvRigger. This is a closed-loop automated system that dynamically diagnoses the agent's policy and synthesizes these components on the fly.
It's like having an automated personal trainer for the AI.
Yeah.
Because a personal trainer doesn't just give you a generic workout. If you have a weak left shoulder, they watch your form and prescribe a highly specific resistance band exercise just for that. And EnvRigger operates entirely as a black box, right? It doesn't require access to the model's weights, and it isn't calculating gradients. It relies purely on trajectory parsing.
Yeah, because if you only look at a binary reward signal at the end of an episode, you learn absolutely nothing about the actual behavioral bottleneck.
Right, you just know it failed, not why it failed.
Exactly. So to extract that diagnostic data, EnvRigger runs the target policy through the base environment for k equals 5 rollouts, just to establish a baseline distribution of trajectories.
And why k equals 5 specifically?
Well, the k equals 5 parameter is critical because it filters out stochastic sampling variance. If you only run one rollout, a failure might just be bad logit sampling, you know?
Right, just a random hallucination.
Exactly. By aggregating 5 trajectories, EnvRigger can parse the logs to identify systemic, repeated cognitive blind spots. The diagnostic LLM within EnvRigger analyzes the action observation history, looking for specific pathologies.
Like what kind of pathologies?
Like, is the agent caught in an infinite loop of invalid tool calls? Is it failing to process dense HTML text? Is it hallucinating state changes that haven't occurred? Once it isolates the exact behavioral flaw, it transitions to the synthesis phase.
Okay, so it maps that behavioral pathology directly to an abstract syntax tree manipulation. EnvRigger essentially acts as a code generation agent, taking the schema of the underlying environment and writing the actual Python overrides for the stages or contracts needed to target that specific flaw.
That's exactly it.
But it can't just blindly merge that code into the training curriculum, right? Because LLM-generated code is inherently noisy.
Very noisy, yeah.
It has to have a validation gate to ensure the mutated environment is actually useful for optimization.
And it does. The validation phase is a secondary k equals 5 rollout, but this time using the newly synthesized wrapper. EnvRigger evaluates the success rate of the agent in this mutated reality.
Okay, so what happens if it fails?
If the agent achieves a 0% success rate, well, the wrapper has likely made the task mathematically impossible, or it broke the logic chain. So the component is either refined or completely discarded.
Makes sense.
On the other hand, if the agent achieves a 100% success rate right away, the mutation is too trivial. It provides no optimization pressure. The system selectively accepts wrappers that sit perfectly in the agent zone of proximal development.
The Goldilocks zone.
Right. Environments where the agent initially struggles, which exposes the targeted flaw, but it can ultimately solve the task if it alters its reasoning trajectory.
Let's ground this abstraction a bit by looking at the specific pathologies EnvRigger caught in actual production models, because the paper lists some great ones. Let's start with the SWE-Bench verified dataset. This is a highly complex software engineering benchmark involving real-world GitHub issues. What specific behavioral flaw did the diagnostic loop isolate here?
So the trajectory parsing revealed a really pervasive instance of reward hacking, or, well, at least extreme laziness on the agent's part.
Laziness. How so?
The agent would parse the GitHub issue, synthesize a code patch, and immediately execute the submission action. It was entirely bypassing the execution of the test suite.
Oh, man.
It just assumed its patch was correct and tried to brute force a passing grade without verifying its own work at all.
It was functioning exactly like a junior developer trying to push straight domain without running local tests.
That's hilarious.
It really is. So to fix that, EnvRigger synthesized a contract that intercepted the final submission command within the Dockerized execution environment. It basically parsed the agent's bash history, and if it didn't find the test command execution, it blocked the submission entirely and returned a synthetic GitHook error.
Yes.
It said something like, verify tests failed. Run the test suite before submitting.
And that intervention forces the policy to internalize a rigorous engineering constraint. We actually see a similar behavioral correction in the WebArena benchmark, which tests autonomous web navigation.
Oh, right. What was happening there?
The baseline models were repeatedly failing data extraction tasks because they were attempting to fulfill the prompt based exclusively on the initial viewport. They were not executing the scroll action, which meant they were entirely missing DOM elements located below the fold.
They were treating an interactive web page like a static image.
Exactly.
So EnvRigger deployed an action space contract that monitored the trajectory history and actively blocked any final extraction command until a scroll action had actually been logged.
Right, forcing them to look around.
But I think the more fascinating WebArena intervention addressed context window degradation during data filtering tasks.
Oh, definitely. The context window issue is a massive hurdle when agents interact with complex e-commerce backends. In one specific task requiring the aggregation of ordered data, the baseline agent adopted an incredibly inefficient strategy.
What was it doing?
It was manually clicking through paginated tables, attempting to count individual rows across multiple pages. And as the HTML DOM state continuously appended to the context window, the attention mechanism degraded. The agent just completely lost track of its count.
Which is such a human mistake, honestly. And EnvRigger identified that the agent was ignoring the built-in filtering tools of the database. So to correct it, it synthesized a stage component that manipulated the initial URL parameters during the reset function. It forced the environment to load with the date and status filter UI, heavily expanded and prioritized right in the initial accessibility tree observation. It aggressively hinted at the optimal pathway, forcing the agent to learn how to execute SQL-style queries via the UI to isolate the data, rather than just relying on manual pagination and, flooding its own context window.
And the empirical results of these interventions are highly compelling. The paper evaluated EnvHarness across 5 distinct evaluation frameworks. So we have ALF World, WebArena, SWE-Bench Verified, Office QA, and SpreadsheetBench.
A good mix.
Yeah, and the framework consistently outperformed domain-specific environment generators. On held-out, zero-shot ALF World instances, policies optimized on EnvHarness wrappers demonstrated a 9.0-point absolute improvement in task success rate.
And the performance metrics on SWE-Bench Verified present this fascinating paradox to me. Because by increasing the friction of the environment, by deploying contracts that actively block lazy submissions and force the agent to run testing suites, the overall efficiency of the agent actually improved.
That's the best part.
The average execution steps required to solve a repository issue dropped from 53.6 down to 49.6. By constraining the action space and forcing disciplined reasoning, you effectively prune this massive search space of undirected, wasteful commands.
You do. Constraining the environment prunes the branching factor of the reasoning tree. You eliminate the compute wasted on repetitive error loops or, the submission of broken code. The system streamlines the trajectory. And what makes this architecture particularly robust is its adaptability across completely different model architectures.
Oh yeah, they tested a few, right?
They did. The authors ablated the pipeline across Gemini 3.1 Flashlight, Gemini 3.5 Flash, Qwen 3.6 Tri-100B, and Claude Sonnet 4.6. The behavioral diagnostics and subsequent mutations shift dramatically depending on the specific logit distribution tendencies of the baseline model.
The contrast between the Qwen architecture and Gemini Flashlight is probably the best example of that in the paper, because the baseline Qwen model exhibits high variance in its autoregressive sampling, which led to massive undirected flailing in the environment.
Oh yeah, just doing random things.
It was averaging nearly 70 steps per episode, executing just random bash commands or API calls, trying to stumble into a success state.
Right.
And EnvRigger diagnosed this lack of focus and deployed tight contracts that heavily penalized invalid actions, which provided the structural boundaries the policy desperately needed.
Yeah.
It literally halved the step count down to roughly 37 steps while simultaneously increasing the success rate.
It actively suppressed the high entropy exploration. Now, Gemini Flashlight exhibited the exact opposite pathology.
He was too timid.
Exactly. As a highly distilled model, its probability distribution would collapse early in the trajectory when faced with complex friction. It averaged only 36 steps before executing a termination command, effectively just giving up.
Wow.
So for Flashlight, EnvRigger generated stages and contracts that incrementally increase the horizon, forcing the model to persist through intermediate failures. The average step count for Flashlight jumped to over 50, accompanied by a significant climb in the success rate. So the environments were custom-tailored to teach a weaker model how to maintain goal persistence.
Which is incredible. And that brings us to the most technically significant aspect of the paper, I think.
Yeah.
Integrating EnvHarness into an active reinforcement learning loop.
Yes, the RL integration.
This isn't just a data generation technique for supervised fine-tuning or DPO. The authors prove that the dynamic state distributions generated by EnvHarness provide a stable, continuous optimization signal for online RL algorithms, specifically using GRPO or group relative policy optimization.
And the integration with GRPO is what elevates this from a clever heuristic to a truly scalable training architecture. GRPO is highly efficient because it eliminates the need for a separate critic model to estimate the value function.
Right.
Instead, it calculates the advantage by generating a group of outputs from the same prompt and normalizing the rewards within that group. But GRPO has a known vulnerability, which is mode collapse.
Mode collapse.
If you are optimizing against a static environment, the group of outputs converges way too quickly. The policy discovers the singular optimal trajectory for that specific MDP, the variance within the group drops to zero, the advantage estimation flattens, and then the KL divergence penalty just halts any further learning.
The optimization landscape effectively becomes a local minimum that the agent can't escape, purely because the environment never pushes back. And EnvHarness solves that mode collapse problem by constantly shifting the underlying state space.
It does.
Because the stages and contracts are dynamically mutating the initial distributions and interaction rules, the agent is continuously forced out of its converged behavior.
The environment essentially becomes a moving target. By updating the wrapper components at regular epoch intervals during the RL run, EnvHarness ensures that the on-policy rollouts remain highly diverse. It maintains healthy variance within the GRPO groups, which keeps the advantage signal-rich and mathematically robust.
That makes total sense.
The paper demonstrated that policies trained with GRPO directly on EnvHarness mutated environments consistently outperformed policies optimized strictly on the original static environments. They achieved higher generalization on held-out tasks without suffering from reward over-optimization.
So we are looking at a fundamentally different paradigm for policy optimization here. We were basically moving away from static datasets and frozen MDPs toward a system of continuous coevolution.
It really is coevolution.
EnvHarness autonomously observes an intelligence, mathematically diagnoses its hidden cognitive bottlenecks, and dynamically mutates the physics and rules of the simulation to aggressively target those exact weaknesses. It is a bespoke adversarial reality engine built entirely for the optimization of a specific neural network.
It guarantees that the learning policy is perpetually operating at the exact edge of its capability curve. The environment prevents the model from collapsing into lazy heuristics, but because of the EnvRigger validation loop, it also prevents the model from being overwhelmed by mathematically unsolvable tasks. It is basically the automated stabilization of the optimization gradient.
It fundamentally changes how we think about the relationship between an agent and its environment. And it raises an incredible question regarding the future of human-computer interaction, I think. Because if this architecture, an adversarial reality engine that autonomously diagnoses cognitive blind spots and mutates the environment to force the user to confront their specific weaknesses, if that proves to be the most efficient method for optimizing artificial intelligence, what happens when this exact framework is applied to educational software or digital interfaces designed for human learners?